Today we're going to find the derivative of functions using the limit definition. Find the slope of the tangent lines through the given points for the function. Slope of a tangent line is the same as derivative. Remember that in the last video we created a definition for finding the derivative, and so that's what we're going to use to find the derivative of this function. The limit as delta x approaches 0 of f of x plus delta x. This means anytime you see x, or the input of the function f, you will plug in x plus delta x, not just x. So every x or input is replaced with x plus delta x, or t plus delta t, or whatever variable you're dealing with. So f of x plus delta x.
Look at this. I'm getting 2 invalid card.
This would be the input squared, so x plus delta x plus 1. This is what we'll plug in. X plus delta x squared plus 1. And then we will subtract the f of x function. Please do not forget, every single time when you subtract, you're subtracting the entire function, meaning you have to distribute this negative all over delta x. Our next step is to expand the quantity x plus delta x squared. X plus delta x quantity squared becomes x squared plus 2x delta x plus delta x squared. That is being added to 1. Distribute the negative all over delta x. In this next step, we're going to combine any like terms. It looks like several things are going to reduce to 0. Positive 1 minus 1 is 0. X squared minus x squared is 0. So each term that is left has a delta x attached, which is awesome. So then we can factor out delta x, and we'll finally be able to direct substitute 0. Go ahead and factor out delta x. Delta x over delta x is 1, so reduce this expression. At this point, direct substitute 0 for delta x, and we get 2x plus 0, which is 2x. The derivative of f of x, or f prime of x, is equal to 2x. We started off with a parabola, and the derivative is a line, similar to what we explored yesterday while graphing the derivative as a function. Our next function is a cubic, so let's plug this into the limit definition to find its derivative. When we plug in x plus delta x, we have to put it in every input of f. So this would be, if it's x cubed, then it's going to be x plus delta x quantity cubed plus 2 times x, that would be 2 times x plus delta x, our new input, minus our original function. Be sure to distribute that negative. Okay, all of the binomials we're going to expand or distribute in some way. Let's remember the pattern of a binomial cubed. Remembering Pascal's triangle, we go to the third row, which is here because Pascal's triangle starts with the 0th row. I like to use Pascal's triangle. You can also use the binomial theorem or expansion. So 1, 3, 3, 1 are my coefficients to start off. And the exponents will always add up to this number right here. The first term is a, so that will be to the power of 3, which means b is to the power of 0. Now a descends and b ascends, so a squared times b to the 1. A to the 1 times b squared. And a to 0 times b cubed. All of these are adding because it's a sum here. So a plus b quantity cubed actually simplifies to be a cubed plus 3a squared b plus 3ab squared plus b cubed. I would encourage you to write this somewhere where you can easily access it and eventually to memorize it. So this is the type of expansion that's happening with x plus delta x quantity cubed. So we should get the first term will be cubed, so x cubed plus 3 times the first term squared times the second term, so delta x, plus 3 times x to the 1 delta x squared plus delta x to the power of 3. That's just the first expansion. Distribute this 2 plus 2x plus 2 delta x, and distribute this negative 1 minus x cubed minus 2x. All of this is over delta x. Woo, let's reduce or simplify anything that we can in the numerator. So we have a positive x cubed and a negative x cubed, that is 0. We have a 2x and a negative 2x, that's also 0. That leaves us with only terms that have delta x in them, which is extremely convenient for us to factor out and reduce. And none of the terms with delta x in them actually combine. So go ahead and factor out delta x. Delta x divided by delta x is 1. So the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x plus 2. And now we can use the direct substitution, 0 for delta x. So you're left with 3x squared plus 3x times 0 plus 0 plus 2. So f prime of x, the derivative of the original function, is 3x squared plus 2. We started off with a cubic function, so it makes sense that the derivative would be a parabola, a quadratic, based on the pattern we've seen. Find f prime of x for f of x equals square root x, then find the slope at 1, 1, and for 2, discuss the behavior of f at 0, 0. Let's plug it into the definition for derivative. F of x plus delta x, so anytime there's an input, as in x, we will replace it with the quantity x plus delta x. So the limit as delta x approaches 0 is f of x plus delta x, so instead of square root x, it will be square root x plus delta x, minus the original function, which was square root x, over delta x. At this point, direct substitution will give you an indeterminate form, so we have to rationalize the numerator. Rationalizing the numerator means getting the radicals out of the numerator and into the denominator, which seems counterintuitive, but at this point, calculus is a little bit more lenient. They don't care if you leave the radical in the denominator. In fact, the textbook that we're using leaves the radical in the denominator many times, but I will always show you how to rationalize it for practice. So we're going to multiply by the conjugate, which is the same two terms, except we change the sign between them. So square root x plus delta x plus square root x. We're going to distribute that. Square root x plus delta x times square root x plus delta x. The square root is removed and we're just left with x plus delta x. When you multiply the outer and the inner terms, they will cancel to 0, reduce to 0. So we will multiply this by this, negative root x times positive root x, and we will get negative x. All right, that's our numerator because that middle term reduces to 0. That's the whole purpose of multiplying by the conjugate. All right, in the denominator we have delta x multiplied by this quantity. In the numerator we have x and negative x. That reduces to 0. Delta x over delta x is a special form of the number 1, so that will reduce. And at this point, I believe we can use direct substitution without getting an undefined expression. 1 over square root x plus 0 plus square root x. This is 1 over square root x plus square root x. Square root x plus square root x, that would be 2 square root x, so 1 over 2 square root x. The textbook leaves it with the radical in the denominator. I know it feels against everything you've been taught, but when they're asking simply for the derivative, I would accept this form. However, if you would like to see it rationalized, we're going to multiply by root x over root x, and our rationalized form would be root x over 2x. Okay, these are two different forms for writing the derivative of the function. The original directions asked us to do a few more things, such as find the slope at these specific points. So finding the derivative gives you a function that you can plug in to find the slope at any specific point. So the points we were supposed to do was 1, 1, and 4, 2. So for this function, we're going to plug in 1, 1. So we're going to plug in 1, and we're going to plug in 4. I'm going to use the one that's unrationalized, just because it seems like less work to do. Okay, f prime of 1 is equal to 1 over 2 times square root 1. That is 1 over 2 times 1. Okay, so it appears as though the slope at 1, 1 is 1/2. At 4, 2, when we plug in 4 to the derivative function, 1 over 2 times the square root of 4, which is 1 over 2 times 2. The last thing it's asked us to do is to consider the behavior that's happening at 0, 0. So we're going to plug in 0 now into the derivative. F prime of 0 is equal to 1 over 2 times the square root of 0, 1 over 0. That's undefined. When your slope is undefined, what does that mean for the tangent line? or the line whose slope is undefined, that is there are actually restrictions to the domain of the derivative. It cannot equal 0. It can't equal a negative. So when you give the derivative, if you have something that could possibly require restrictions, then make sure you write that. X must be greater than 0. X must be greater than 0. Here we have the conclusion for this problem. All right, let's do one more example. Find the derivative with respect to t for the function y equals 2 over t. If you're more comfortable referring to this function as f and x, you can go ahead and do that. That's what I'm going to do. If you do use t, make sure you're using delta t in your limit definition. F prime of x is equal to x plus delta x will be plugged in anytime there's an input in the original function. The original function is 2 over x, so instead of x in the denominator, we will write x plus delta x minus the original function, which is 2 over x, all over delta x. When we have a complex fraction, it often helps to combine the many fractions, whether they're in the numerator or the denominator, get like denominators and combine those fractions so that you have a fraction divided by a fraction, which you can change to multiplication and hopefully reduce. The denominator of this mini fraction is x plus delta x. The denominator of the other mini fraction is x. So my LCD is x times x plus delta x. Go ahead and multiply these fractions. This one will be multiplied by x plus delta x over x plus delta x because that's what its denominator is missing. That's in the LCD. And this one will multiply by x over x. Our many fractions now have the same denominators, so we can combine the numerators. Please don't forget to distribute this negative. Okay, so go ahead and distribute a negative 2 into this parentheses. Minus 2x minus 2 delta x. This is over x times x plus delta x, all over delta x. 2x minus 2x is 0. We have negative 2 delta x over x times x plus delta x, all being divided by delta x over 1, you could even say. Let's change this division of fractions to multiplying by the reciprocal of the denominator. So we should have negative 2 delta x over x times x plus delta x times the reciprocal 1 over delta x. All right, delta x over delta x is equal to 1. We now have something we can direct substitute into. Negative 2 over x times x plus delta x. Go ahead and plug in 0 for delta x. Negative 2 over x times x plus 0. Our derivative is negative 2 over x squared. And that's the derivative, the slope of the tangent line.